Well, thank you, Rachel. It's my pleasure to be here. I am not an astronomer or an astrophysicist, but I met Rachel through a mutual friend in the UK. And so she asked me to come interlope and talk about dinosaurs. I was given this title, and we're going to come back to it at various points in the talk. How space rocks killed the dinosaurs. All right, so let's look at this a little more closely. This just sums up my talk today. And it's sort of a kind of Texas themed. In my office, I have a picture of a dinosaur with cars suckling on its teats. And I like to remind my colleagues that where gas comes from, which is, of course, fossils and dead organic matter. So let's look a little more closely and get started with defining some terms. So we're going to start with one that I bet you think you all know the answer to. So we're going to start with dinosaur. So dinosaur, we can look at what it comes from, its etymology, fearful or terrible lizard. Does that help us? Now, this is an audience participation. We're not going to set anything on fire. Please don't do that. But I would like you to vote visually and vocally for whether or not what I show you is a dinosaur or not, okay? You with me? All right. So if it's a dinosaur, raise your hand and say yes. If not, do not raise your hand and say no, okay? All right, here it is. Yes. All right, good job. Okay, we got some mixture. The yeses took it. No. All right, universal no. Good job. This guy. I like to see this. A little bit of, there's some yeses, some nos. How about this guy? Yes. All right. Well, we barely need the beginning of my talk then. In fact, the only two dinosaurs I showed you were the Stegosaurus and this well-armed chicken. Everything else is not actually a dinosaur. So just to make sure we're on the right page, Dinosauria is a very exclusive address in the tree of life. So if you are descended from a common ancestor on one tiny twiglet of the tree of life, then you are a dinosaur. And in fact, one part of dinosaurs are birds, which are feathered. And so this is something that we're going to come back to today, giving you a sense of some of the characters that we have accrued, some of the features of dinosaurs that link them and tell us that birds are living dinosaurs. They're ones from all over the skeleton, but some include the wishbone here shown on a T-Rex and the wishbone here on a living dinosaur. So we have many, many of these features from the bony skeletons of dinosaurs and of birds. But if we take another look at evidence that we've had just since the 1990s, 1996, coming out of quarries like this one in northeast China, we see a whole new set of evidence that I've been kind of involved in working with over the last, is that 20 years, that comes from these rocks that we break open like books from these ancient lake deposits. And what they've shown us are remarkable things. In fact, not only do we have these dinosaurs from the Cretaceous that have bony features only seen in living birds, but they have feathers. So these are some of the incredible dinosaur discoveries that we have made just in the last, these are from the last couple of years. So you see here feathers on the wing and on the leg, down at the bottom, really remarkable. And this is a reconstruction where we've been inferring the color of these dinosaurs, which is not the topic of today's lecture. So just to give you another glimpse of this new kind of fossilized soft tissue evidence that further links these small raptor dinosaurs with birds. When we were working on this reconstruction, I had some local inspiration. I bet you guys can't guess what that was. So other dinosaurs had fuzz rather than full-born feathers. This, we think, is a more primitive structure. And just to show you some of that fuzz on a couple dinosaurs, this one we published last year. And then this guy, little pony-sized Tyrannosaurus from China, discovered about 10 years ago. So we're moving on. This guy is a living dinosaur, right? Dinosaurs are not extinct. They are very much with us today. And in fact, feathers, I know I like that, someone's enthusiastic. And feathers don't make the bird. We have lots of non-bird dinosaurs that have feathers. Let's just sum that up. So we have all of our, this is what we call them, non-avian dinosaurs. They all went extinct. This is kind of a wimpy laser pointer. They all go extinct at where we're going to get next, the mass extinction at the Cretaceous-Paleogene boundary. That's what you've all heard about. And some flying dinosaurs also go extinct around that time. Before that extinction begins the radiation of living dinosaurs, which are today the most species-rich group of terrestrial vertebrates. We're mammals, we think we're really important, but birds dwarf the diversity we see in mammals. So that is, dinosaurs dwarf the diversity seen in mammals. All right, let's get to the main topic of what I was asked to talk about today, which is space rocks killing dinosaurs. Well, we know that's only part of dinosaurs that they're going to knock out. So here's what goes extinct around 66 million years ago. There they are. So all of our non-avian dinosaurs gone, and a lot of other cool things like pterosaurs, marine reptiles. And some of these groups are on the decline in species richness before the actual boundary itself. So we're going to come back to what might explain that. But first, we need to further define what we're looking at. We have survivors. So we have parts of Dinosauria that make it through, things like ducks, things like relatives of ostriches. This is a very weird reconstruction of a small mammal. So these things survive. And so that's actually going to become a quandary when we look at evidence for what happened around this time period 66 million years ago. So mass extinction. Well, where do we see mass extinction in our kind of everyday life? We see it at the movie theater. So we've got deep impact, volcano, etc., and we think of these things as devastation, and they're not far off in that. But we, as scientists, look at mass extinction and we have a precise definition. And what that definition is that the rate of extinction exceeds the speciation rate. And it does so in a level greater than background extinction. This is important because you might have seen that a lot of people are talking about how we're in a mass extinction right now. And it doesn't look anything like this. So why do we say that? We say that because extinction rates are estimated to be much, much higher than the background rate and then the speciation rate in the present day. So this is a Primitivo plot from 1980, the first kind of study looking at quantitatively what mass extinction would look like, and it's these peaks, and when these peaks occurred in geologic time. These snappy dressers were the ones that in 1980 did this study, and what they found was that here's the number of, kind of a proxy for the number of species on Earth through time. Here we are. And they saw these precipitous dips that occurred on very short timescales. And they did not coin the term mass extinction, but they referred to these as the Big Five mass extinctions. Now, they're following on a distinguished trend. This is a plot from 1860, a little-known plot which was looking at the number of species in the British fossil record. And what we see are precisely some of those same patterns that we found many years later. These dips at the end of the Paleozoic, and again, around 66 or 65 million years ago. So, in fact, these very patterns, these very mass extinctions, are what mark out our geologic timescale. That's why we have these different units of geologic time. So, modern mass extinction studies, and I always like to remember this because science is always in a social context, and modern extinction studies really date to the Cold War. So, although we've had some blasts, maybe we can recall that the kind of thinking about nuclear devastation was driving a lot of studies of what would happen if you massively perturb the Earth environment on very, very short timescales. So mass extinction, in fact, was a term coined in 1962. It was coined by M. Newell for crises in the history of life. The same year, the Cuban Missile Crisis. 5 years later, the ratification trying to control nuclear proliferation overall. So there's a profound interest in modeling from the physics side of it, impacts and blowing stuff up, and how it affects living creatures. So that's the modern context for extinction studies. So just to sum up the second part, we've always known that there were changes in the diversity of life through time. That's where our geologic timescale came from. But mass extinction is in fact a relatively recent concept. All right, let's get on to space rocks. Can they take all of the credit for the extinction of non-avian dinosaurs and other cool things like pterosaurs? So what do we know? 65, 66 million years ago, an estimated 47% of life goes extinct. These snappy dressers, and this is around the same time, this is in 1980, find a sequence here. This is in Gubbio, a beautiful medieval town in central Italy, and it's right outside there, and you see this very thin layer. And in this layer, they found a very, very high enrichment of iridium. And this prompted them to publish this incredibly influential paper, An Extraterrestrial Cause for the Cretaceous-Tertiary or Cretaceous-Paleogene Extinction. Well, this was started people looking all over the world for more of these boundary sequences, and indeed they found the same iridium enrichment all over. So far southern hemisphere, global effect. In North America, where the sequences that are shown here, we also see burn layers. So evidence for profound wildfires, and this is a lot of the big burn or coal layers are associated in North America. We'll come back to that in a second. So what is some of the other evidence for an impact event at 66 million years ago? Well, we got these spherules. So these are ejecta, very, very tiny ejecta that went very far distances. They don't have a global distribution, but they have an extensive northern hemisphere distribution. And then we have tsunamites. These can be found all along the coast of Texas, down in where exposed, and then all into the Bahamas and that region. We find tsunamites, and we'll come back to why, right at this boundary event as well. We have shocked quartz. That means force went through these quartz crystals. They were shocked by the shock waves coming out of this impact event at such a level that they actually permanently modified the crystalline structure of that quartz. And it can only happen with you drop a couple nuclear warheads or you have an extraterrestrial impactor. In fact, they tried to generate these from volcanoes, and the volcano would have to be like super enormous. So it's not a volcano. So what else? Shortly thereafter, a structure that had long been noted right on the tip of the Yucatan Peninsula. Now, this structure actually is ringed by sacred cenotes. Maybe some of you have swum in them. They're deep swimming holes all in the Yucatan. They ring the outer part of the crater. So you can swim in what is the former, evidence of the former crater, outer crater wall. Yay! So this is the gravity anomaly associated with the structure today, and it was only a little later that we had really good dates tying this precisely to when we see all of this extinction. So we now, in terms of our present day knowledge, this 10 to 12 kilometer in diameter asteroid or comet, and maybe someone here can speak to that, but I've heard asteroid or comet, crashed into the Yucatan platform and formed this approximately 200 kilometer diameter Chicxulub crater. So what we have here now is we want to look at the effects of that. We want to look at what we call, very colorfully, our kill mechanisms. So it sounds really badass, and it is. So we've got a lot of kill mechanisms. And when I started studying this early in grad school, it was like, how could anything survive? So we've got fires, North America, earthquakes, tsunamis, shock waves, molten rock flying from the sky, bursts of ejecta going up through the upper atmosphere, becoming globally distributed. So we've got a lot. This is, in fact, a more recent list of all of the kill mechanisms that we have. Regional effects up here, short-term stuff, burning, soot, acid rain. This is an incredible list of perturbations on very, very short timescales of the Earth system. And I'm going to come back to that. This is a very short-term perturbation of the Earth environment. What matters with impacts? The Earth is being impacted every day. We are being hit. What matters? Size matters. So we've got, estimates for the size of the Chicxulub impact versus an impact that was witnessed by humans in kind of Siberia. And what we see is that the diameter of that crater and estimated impacts really increase rapidly with size. This is another Primitivo drawing, but what it's showing, if you like geology, the undersurface of where the impact occurred. And so what we think another thing that really matters in how devastating an impact is what are the characteristics of the subsurface, what is being impacted. And so there's estimates that a lot of sulfur was released when, in this particular case, because of the rock types that are being hit by the impactor. Another thing, and my major professor in college at Brown studied this phenomenon and proposed that the angle of the impact really mattered, and that it would have differentially shot most of the ejecta and the burn and the kill over North America, where the best studied sequences of rocks were found and where this boundary had been studied. Yay! So I know, lucky for us, but what we found, I work in Antarctica on another sequence close to the KT boundary, and what we find is that we don't see as abrupt effects in the high southern latitudes. So I actually support a differential kill hypothesis where the northern hemisphere is differentially impacted. So we're going to conclude today, it's not just about space rocks. So what's in vogue right now is really looking at the impact of volcanoes. So this is a recent study looking at this is different mass extinctions through time. Here's the PT, which is really one of the biggest in the history of life. And then this is the KT. And these are known volcanic events, including large igneous provinces or lips, which I'm going to come back to in a second. Here's the Chicxulub impact. And while in the 90s, impact events were really emphasized as kills for mass extinctions, now there's a lot closer look at these large igneous provinces. Well, what are they? They are not a normal volcano. These things produce incredible amounts of low viscosity lava, if you will. They move very fast, they build up really quickly, and you have a lot of volatiles and a lot of these things that are released with these major, these lips. And we can look for proxies for them, we can look at carbon isotopes, we can look at some people are exploring these other systems to detect the impact of these things globally in the fossil record. So right around the KT boundary, in fact, starting about 10 million years before the extinction of the dinosaurs, we have the emplacement of this massive flood basalt, this large igneous province in India. So you can see where it is here. This is a huge region. All of this is flood basalts. And it goes almost I think it's over 1 kilometer in height, this sequence of flood basalts. All of these large igneous provinces and large volcanoes can have the same kinds of effects that we see in an impact event. And what we're talking about is rapid global perturbation of the Earth system. So here are some of the baddies that come with lips. And here's a summing up, again, of what would happen on short time scales and long time scales in these events. And so we know that the Deccan is occurring around the time of the extinction of the dinosaurs, and we know that the bolide impact seems to be like the coup de grace and really deliver, kind of finish out this sequence. So there's a lot of nuanced work looking at whether the deccan is really diminishing or eroding the Earth's environment, and then the impact event happens, and then nobody has a shot. So in conclusion, what I want you to take away from this talk, besides dinosaur fun and feathers and stuff like that, is that what are mass extinction events? So they are these massive, rapid changes in the Earth system, environmental perturbation that is global in nature. And what we have a hard time studying is how we relate this perturbation to biotic consequences. And this is a real issue in the present day, and it's an even bigger issue in the fossil record. And so in the fossil record, when we're trying to look at these things 65 million years ago, we have this issue that, in fact, so many kill mechanisms have been proposed from the impact and from these large igneous provinces that you wonder, how could anything survive, right? How could anything have made it through? And so we are looking at modeling those events and what, is it more of a regional effect where life survives, et cetera. So with that, I hope I've taken your notion of dinosaurs from this uncomfortable image to a much more dynamic one. And with that, I'll just say a final thank you and open it up to questions.
Okay, we have time for a couple of questions. I see someone leaning way over the railing up there. Yes, sir.
Considering that North America was the most affected by the meteor, do you see a difference in the species in North America today versus?
So the question was, given that the impact event happened in North America, do we see kind of holdover effects in biodiversity today? And I would argue probably not so much, because a lot of groups that went nuts right after the KT boundary or right before it, mammals and birds, are globally distributed. And what's really shaped North America, and this is other stuff I work on, is global cooling from we used to have a greenhouse Earth with no polar ice caps to the present day. And that's really, really shaped animal distributions. So I would say probably not. But what it did do is groups of dinosaurs that differentially lived in the northern hemisphere, like Triceratops and its kin, for example, all those guys get wiped out because they really weren't, they experience, they're hugely species rich and they're just gone in apparently a very, very short time scale.
Oh, poor Triceratops. All right, Dawn, right here in front.
So there was no paleo landmass. It was a shallow carbonate platform covering this basement rock that was really sulfur rich. That's why all that sulfur was put. So it's a shallow carbonate, like shallow sea. I don't know, because it has to do with how many volatiles it's sending up, what it's volatilizing. So it's impacting into this rock, and then it's sending all this junk into the atmosphere, and that kind of thing. So I'm not sure that it necessarily would be worse into land, but if there's an expert on that in the audience, we can.
Let's go straight here.
Yeah, just to put a scale to it, curious, did it change the length of the day or the length of the year much?
So not as far as I know. An impactor of this size would not change the rotation of the Earth. There are some really early impact events. I'm talking like early Paleozoic and those, like some of those craters where people argue about it more. And we have astronomer, we have people who can speak to that. Yeah, I don't know. So no, in terms of, I don't think it changed anything about rotation.
All right, one more quick question. Up here.
What is the name of the panda-colored dinosaur?
Okay. What is the name of the panda-colored dinosaur? Oh, the one that was fuzzy? A Sinornithosaurus. Yay, but it wasn't, that one wasn't actually panda colored. Our whole point of our paper last year is we can't reconstruct the color of fuzzy dinosaurs, but we can reconstruct the color of ones that have feathers like birds. So sorry about that. I don't know if it looked like a panda or not.
Dinosaurs and birds share any other attributes like
Tons.
feathers, but like singing or
Oh, working on the singing right now, but like we think some modicum of warm-bloodedness. We definitely know they slept like birds with their heads tucked under their, little arms, and then we also know that they brooded eggs like birds today as well. So we can find those things in the fossil record, and probably a lot more in the next 10 years. So good question. All right, thank you guys so much.
Thank you,
and my
Dr.
pleasure.
Dinosaur Feathers.